Hey there, today we're going to be looking at loudness, how we measure loudness of sound. And the way we measure loudness, the scale we use, is called the Bell scale. It's named for Alexander Graham Bell. Okay. Now, this is not a linear scale, it is non-linear. And you are very familiar with linear scales. Linear scales, like the meter stick, you have 0 at one end, 100 at the other, and halfway in the middle is 50. Well, this is a nonlinear scale, and this doesn't work that same way. So in the Bell scale, what we have is we might have a 0, 1, 2, 3, 4, 5, 6. There's no end to this. And the first thing you want to know is that 0 is not silence. 0 is called the threshold of hearing. Threshold of hearing. And it is the quietest thing that anyone could hear. But it's not silence. And then what you get is 1 is not 1. What these numbers represent is they represent exponents because it's such a ginormous scale. And so 1 is really 10 to the first, and 2 is really 10 to the second, and 3 is 10 to the third, 10 to the fourth, and so on. So up here we have 10 to the eighth, and it continues on. So in essence, when you have 1 on the Bell scale, that is really 10 times louder than the threshold of hearing. Whereas a 2 is 10 to the second or 100 times louder. 3 is 1,000 times louder. Okay? So this is not a linear scale. Now you're familiar with other nonlinear scales. For example, earthquakes, that's another type of wave, and it is measured. One of the measuring scales is the Richter scale, and the Richter scale is also very similar to this. And so you may say, well, we had an earthquake of a 4 and somebody else had an earthquake of a 5. Theirs is a little bit bigger. No, a 5 is 10 times bigger than a 4. And an 8 is 10 times bigger than a 7. So these nonlinear scales are quite a bit different than what you might be familiar with. Okay, so we have to deal with them a little bit differently. Now, in the Richter scale, because it's such a big difference between a 4 and a 5, they will actually measure to the tenths place. And so you might say, oh, we had a 4.1 as opposed to a 4.7. Well, that's a significant difference. Between a 4 and a 5 is 10 times the intensity. You want to go even farther yet to a tenth of a place. So we do the same thing, but in the Bell scale, but we do it a different way. In the Bell scale, we measure to the tenth of a bell. And the reason is 1/10 of a bell is about the limit to what a human can distinguish. So if you heard a sound at 4 bells, and then you heard something at 5, well, that would be 10 times louder, easy to tell the difference. But if you heard 4 and 4.1, that's right at the limit of what you could hear, because a tenth of a bell. Now, instead of us going to the tenths place, what we do is we refer to the decibel scale, and deci in the metric system is 1/10. And so that's what you often hear of decibels. That is really decibel. It's the Bell scale, and we're going to 1/10. And so 1 bell is the same as 10 decibels, and 2 is the same as 20. So you just add a 0 on these, and all of a sudden you may say, oh, I recognize this. You're right, this is the decibel scale, which is decibel. And so what can be confusing is you might say, well, how much louder is 50 compared to 40? Well, the difference between 50 and 40 is 10 times. And then you might say, well, how big is 60 compared to 40? And you might say 20. No, it's not. It's 100 times, because you have to, once again, you have to go back to the Bell scale. And that every one, a 4 goes to a 5, that's a factor of 10, one factor of 10. A 4 to a 6 is 2 factors of 10. that is 100 times bigger. Okay? So there's a simulation I want you to use, the Google in the decibel scale here. And so these problems are pretty easy. And so we can say decibel rate is 70 decibels. A sound source is 1/1000th the intensity. What is that decibel rating? So we say, oh, that's just 3 factors of 10, but it's less. So 3 factors of 10, not 70, but we would go 60 is 1 factor of 10, 50 would be 2, and 40 would be 3 factors of 10. So this is a 40. We try another one. This is 1, and we got 1, 2, 3, 4, 5 zeros. So we simply say, oh, that's 5 factors of 10, or in essence, 50 decibels less than 90. That would make it a 40. Here, this one here is 1, 2, 3, 4, 5, 6, 7 factors of 10 larger, or 70 more than 50. That would be 120. So if it's bigger, you're simply going by the number of decimal places. So now, when you keep that in mind, say, well, how do we write that mathematically? Well, what we're saying is the change in the decibel level is 10 times the log of that ratio. 10 times the log of that ratio. And don't let logs be scary. It's simply saying what is the exponent. Okay? And the 10 is simply because we're using, instead of the Bell scale, we're using the decibel scale. So now I've got some sample problems here for you to look at. And what we're going to do is we look at the sample problem. We say, oh, it's 1,000 times more intense than a 50 decibel sound. Okay, well, we take the log of 1,000, and we're going to take 10 times that is going to be our change. Okay, well, the log of 1,000 is 3. This is how many zeros there are. And we take 10 times that, and that gives us 30. And since it's louder than 50, it's 30 plus 50. That gives you 80 dB. What if it's 1/100th? Well, we're simply going to take the log of 1 over 100. Now, if you say 100, how many zeros? 2 zeros, but in this case it's going to be a -2 because it's 1 over. We're taking 10 times that, and 10 times that is -20. This is our change. It's not our decibel level, it's our change in decibel level. So now we're going to go to, we'll add that to the 90, and we're going to get 70 dB, smaller. Okay. Now, let's try here. How does 60 compare to 20? Okay. Now we're going the other direction. So the change is 60, that's what we're at right now, compared to 20. And that would be 40 dB. And that is equal to 10 times the log of that ratio. Well, we divide both sides by 10, and we're going to get 4. Now, how do we undo the log? Okay, how do we undo the log? That is simply, it means 10 to the 4th power. And 10 to the 4th power is simply 10,000. It's 10,000 times greater. Okay. Now, we come here and we say, how does 70 compare to 100? Well, 70 is less. Okay, you could just say, well, yeah, it's 30 or 3 factors of 10. Well, what we're looking at is we're simply saying 70, our change, 70, there's 100, so we went down 30, negative 30, and that negative 30 is going to be equal to 10 times the log of what we're after. So we divide both sides by 10, and we get negative 3. Negative 3, well, that means we want 10 to the negative third power. 10 to the negative third power would be 1 over 1,000, or if you'd like to write that in decimal, is 0.001. Okay. Now, more examples like this. The hard ones are a little bit farther down where you've got things like 2,000, and that one, you can't simply do that by inspection quite as well. So let me show you how to do this type here. We are going to take the 10 times the log of 2,000. And this is where we're going to need to use our calculator. Okay, our change in our delta level. Okay, so what we want to do is we want to take the log of 10,000. So let's clear this. And we're going to take log of 2,000. We're going to take 2,000. And we are simply, this button over here on the left is the log button. If you take the log of 2,000, well, log of 1,000 would be 3. So this is going to be bigger than 3. And it's going to be 3.3. Okay? And then what we're going to do is the log of 2,000 was 3.3. We take 10 times that, and we get 33. And then it's more intense, so we're going to add that on, get bigger, and we're going to get 90 dB, 90 decibels, oh, pardon me, 93 decibels. Now, all right, here we have 1 over 4,000, the intensity of 70 dB. So we're going to be getting quieter. So what we need to do is take the log of 1 over 4,000. So if we go back to the calculator, and what we're going to take is 4,000, and we can take the reciprocal of that. That's 1 over 4,000. And then what we want to do is we want to take the log of 1 over 4,000. Okay. Now, we get negative 3.6. So now we have the log 1 over 4,000. We're going to take 10 times that. And we're going to get negative 3.6. 10 times that, of course, will be negative 36. And if you add that on to the 70, you're going to get 34 dB. That sound would be at 34 dB. If we're at 65 compared to 30, we would take the change, would be the 65 minus the 30, which will be 35 dB. But that is equal to 10 times the log of that ratio. So if we divide both sides by 10, we are going to get 3.5. And now what we want to do is we want to take 10 to the 3.5 power. Now, I'm not so good at that in my head, but if I put in 3.5, and now I use the 10 to the X button. And when I do that, I get 3,162. Just keep in mind, the 10 to the X button and the log button undo each other. So if I take the log of this, I get 3.5. If I take that to the 10 to that power, I get 3,162. So this is going to be 3,162 times greater. That's how much louder it is. One more, we do 70 decibels compared to 83. We take that change, would be 70 minus 83. That is going to be a negative 13 dB, which will be 10 times the log of what we're looking for. Divide both sides by 10, and I get negative 1.3. So what I'm after is 10 to the negative 1.3 power, which we know is going to be a small number. So let's keep in mind, we know it's going to be a small number. So I want to put in 1.3, change sign, make it negative, and I want to go 10 to that power, and I get 0.05. 0.05. And that's the ratio. That's how much quieter it is, which is about 1/20th. It's approximately. It's going to actually, there's more on that, but 1/20th is what's going to be quieter by that factor. Hope this helps you.